Hello, everyone. Thanks for coming. My name is Jason. I'm the CTO for Solayer. So today, my presentation is about the progress we've made in the past year. Primarily, I'll do a deep dive on the bridge, which is between Solayer and Solana, two SVM chains, and how do we accomplish that from a technical perspective. Before that, I'll also give the audience a little bit of background about Solayer chain and how is it different. And therefore, going into the bridge discussion, hopefully you have more context about why we're structuring that way, right? So this is probably one of the first presentation on bridging between one SVM chain and another SVM chain. And there are a couple design primitives that we've thought about very hard at before beginning any work. So I'll share those as well. So our office is based in Palo Alto. Before I start, I just want to say that we're hiring as well, especially on the software engineering side. So the current team members, except for, in addition to, me, is coming from SushiSwap, Amazon, and Microsoft. And a couple other, Bay Area companies. And if you have friends or you're interested in joining, learning more about what we're doing, we'll have a booth on the other side of the room. So feel free to talk to us. In addition to Solayer, I'm also the co-founder and tech person for MPC Vault, which is a multi-chain, multi-signature wallet. So a lot of MPC stuff and different abstraction layers for orchestration layers for different chain. We've integrated over, I think, like 20, 30 chains right now. So we're very familiar with how each and different chains work. And that experience also informs chain design as we're building out Solayer chain, which is SVM based. Prior to that, I did some ML and cryptography work. So just to give everyone a highlight or rather a brief rundown of how Solayer chain is different from Solana. The similarity is that both are running SVM. So whatever program you have on Solana should be ported without any issues or needing remodifications, probably some a little bit when you deploy it on Solayer. From a developer perspective, one of the most biggest difference you can notice is our rent cost when you are deploying your contract is going to be 1% of what you will experience on Solana. So this is from a real data because we deployed contracts on Solana as well. So our restaking contract back then, it costed us about $1,200. If you were to do the same thing on Solayer, it's probably just $12, right? So you don't have to care about do you have to raise money? Do you have to hedge somewhere in case the Solana goes down? So all these improvements are made so that it's more developer friendly. And even if you want to just start experimenting with some contract deployment and you can't really get the faucet to work on Solana, because Solana DevNet faucet is actually pretty, it's not very stable. Feel free to come on to Solayer and then deploy your contract here. You should work exactly the same way, right? And there's also, for deployment, you'll also notice, which is part of the characteristics of having this high throughput, is that your transactions wouldn't fail. So if you deploy on Solana, you'll notice that sometimes you have to retry, and the retry logic isn't very explicit. You have to do it manually. So you have to retry it 3 or 4 times in order to fill the buffer to get all the program uploaded, and then you switch the entry point of the program. But on Solayer, you'll notice that the second you just start pressing the keyboard, things should complete in under, like, let's say 1 second, right? So that's generally what we have been experiencing from a developer perspective. The average inclusion time for a transaction is much lower, and we don't have MEV. So the ideal use case is, for example, if you want to have a trading system set up, either meme coin or RWA assets, you don't want to have any front running. You can come to Solayer because we operate a mega sequencer. If there's any front running happening, you can prove that there's a dishonest mega sequencer, right? You can report it to the community and actions can be taken. But we don't have a typical POS system where everyone gets to become a block builder. Now, I think just like what the previous talk has mentioned, there are pros and cons with it. One of the cons is that you can get exploited because people with a lot of stake have the power of including a lot more transactions because they get more block space, and we can reorganize the sequence of transactions to extract value from your transaction. For example, when you're doing a swap, they can put their swap transaction before you and then do a counter swap, like swap back the asset after you swapped. So effectively, that would increase the slippage of your transaction. So no MEV is also a very important, point that we want to stress here. And then the other part is about throughput. Through our mega sequencer design, which I'll, touch upon later, we're able to achieve a sustained 300,000 transactions per second on the mainnet. That's currently live. So you guys can experience it, how that feels like, and the latency, and etc. Now, if you ask me, the most common question I get is, Solana is already pretty fast. Why are you guys building a faster and the chain with higher throughput? What's the use case? Now, the answer is, given what I said earlier, could be, I think it's pretty obvious. There are lots of things that are not covered by Solana. First of all, different parameters of the cost. Do you want to have, for example, gas fee rebate? Do you want to have your own sovereign state? With our SDK, we kind of support that as well. Do you want to have a consistently low transaction inclusion time without MEV risks, right? Running MEV risks. So these are the things that were very different from Solana. And if you're building an application that want to have a different characteristics for your app, I think Solayer is the right, there's enough differentiation for you to say that, hey, here's the right product, right? Here's a different product and here's a different platform for you. In addition to, the commonality is that, of course, there's the same SVM language, right? But the deployment platform will decide on a lot of other things such as MEV and so on and so forth. Just to highlight what we're doing as part of the throughput improvement, some of the common things, this is just the transaction lifecycle. Some of the common things include, SIG verify, deduplication, scheduling. These are all parallelizable. As transactions coming in, you're able to verify the signatures associated with each transaction in parallel because they don't depend on each other, right? The only thing you're saying is that does this cryptographic signature check pass, right? And then you can do that in parallel. Where we do a bunch of work is actually the execution layer. The execution layer is pretty much bound by I/O access and also the compute time of the runtime or the sort of compute time spent on each program execution. What we have done is that we have separated into different executing nodes, and then they are interconnected via a low latency system. We're switching to InfiniBand, still experimenting with it. Today it is not. So that is how we're running a node across different, let's say, computers, as opposed to just running a binary on one single computer. So to understand what we're doing, that's sort of a good way of putting it. And each node are executing different parts of the system because you can have transactions executed in parallel if there's no state conflict, right? If they don't ask for the same resource, they can actually go ahead in different, systems. And then they're interconnected via a very low latency system so that, data packet switching and communications can be done with super low latency, and so on and so forth. One of the important points I would like to touch on is how do we run consensus, right? So we have a mega sequencer, but that doesn't mean that there's no consensus. So we have a very unique consensus system where the mega sequencer does all the sequencing and transaction inclusion and whatever, but we still require a network to actually verify that all these transactions are properly included. By being properly included, what we mean is that the computation and the results are included as per the logic of the chain, right? Which includes how your smart contract is written, so on and so forth. And part of that is done in a distributed way. So imagine you have like 100,000 transactions. You can chop the 100,000 transactions into 10 groups of 10,000 transactions, right? They add up to 100,000. And you give the 10 groups of 10,000 transactions to different people and different groups of people. And they each verify part of it. And then you'll be able to reconstruct from any node's perspective the proof that collectively will prove the 100,000 transactions validity, right? And you can just sign it, and everyone who's in the system, you can choose to verify it, but you can also say that, hey, I trust these other nodes, just like you trust all the other participating nodes in any other decentralized systems. They can just apply the effect of those transactions. Now, the idea there is that applying the effect of a transaction is much simpler than applying the transaction itself, because you have to run it, you have to verify it, and that would include all the scheduling, I/O access, bottleneck, and etc. But if you're just applying a transaction, it's like you're downloading movies from, the movie sites where you're just writing things onto the disk. You're overwriting the state. You don't need to do. You have to do checks just by checking the proof, but you don't have to run the transactions, decode it, sequence it, and then check if that's valid against another source of against another sort of a version of the database. So I want to cover how we're doing bridging from SVM, Solana to Solayer. There are actually 3 steps. The first is what happens on the original chain. And then the second layer is the Guardian network. And the third layer is the destination chain, right? So these are the high-level overviews, but I'll skip to the more detailed page. So the token mapping is what we've come up with to be one of the important primitives, because we don't want the bridge guardians to operate with their own state. So we want to construct a system where for the guardians, we're actually moving the data from one chain to another to have as limited of a state requirement as possible, right? Basically, you can spring up your system with a private key because you're, somehow trusted and you're verifying the system with that. With that key, and you don't have to download whatever database. You can just boot up the system, click start, and then it should run. That's how simple it is. But where should all the data be stored, right? The data should be stored on chain. And probably every single data that's required as part of the bridging operations done by the Guardian network would be deterministically calculated. And they can be derived as opposed to stored and then fetched. Right, so that's something that we're trying to create from this entire system. So the token mappings would have the mint address on Solana and Solayer. But more importantly, the PDA derivation is actually deterministic. So you'll see that the token info PDA account, which is what you use to query this piece of data, is also deterministically derived. So even right now, taking out my laptop and running a Python script, I'll be able to calculate where I can get this data given any 2 mints on Solana and Solayer. So if you're moving something from Solana to Solayer, the Solayer mint is also deterministically calculated, which I'll show the equation later. The rough process in terms of going from Solana to Solayer and going back from Solayer to Solana is this. Going to Solayer, it's lock and mint, and going from Solayer to Solana, it's burn and release. And there are specific stuff that we have put in place from Solayer to Solana. In terms of the burn and release flow, we've also added a step number 5, which is a rate limit check, what we call bridge cap. And we do this for risk purposes. If the amount of value that flowing back to Solana exceeds a certain value, it might trigger a manual investigation. It's actually a time lock. So past that time lock, the money will be able to go back to Solana automatically. But if anyone raises a red flag about that transaction can be stopped. And this is because if you analyze all the hacks out there about bridges, the most important thing is you can fabricate a proof and submitting to the original chain bridge such that it tricks it into thinking that I can release all the funds to a certain address. And that's where the biggest risk is with bridging. So we have done a lot of, we've had a lot of thinking around that. But this is, just the threat model is that if anything happens on Solayer, even in the case of a contract mis-execution because we placed a primitive, in a wrong spot or whatever, or the bridge itself is hacked, for example, key leak, right? Just, if we were to isolate all the risks, we'd be able to stop that attack immediately. And this is one of the most important considerations of building a bridge. So just now I said about how do you get target mints, and this is more of a specific way of calculating that program-derived account. So if you follow that, everything is done in a deterministic way. So for the last few seconds, I just want to show metadata lookup. One of the tricky thing is how do you also include the metadata when you bridge the chain over, right? So there has to be a lookup process. And the lookup process is such that on Solayer side, we actually check if the token is bridged. And you can do that again in a deterministic way. So there's a function which you can call, it's called is mint bridged token. And the way to check it is to check if the mint authority is the bridge handler. And if the mint authority is the bridge handler, it means that you're able to determine that this is a bridged token, and therefore you should follow a bridged token metadata lookup. And if not, there's a native token metadata lookup. So there are a couple slides. I think the slides will be available for you guys as well. But here's a more of a longer version of exactly what happens under the hood. And with that, that's my sort of presentation. I'll be around at the booth. Happy to talk to folks who have questions. Thanks.